Hello, welcome to Empowered Learning. This video will be about the derivation and demonstration of Newton's method. Newton's method is just a numerical method technique used to find roots of equations. Another way to put that is we use Newton's method to solve for x-intercepts of functions. And when we say numerical methods, or numerical method, all we mean is it's just an iterative method that we can actually program into some kind of software or computer to be able to do these calculations for us if need be. And we're actually going to see that during this particular video. So we see that Newton's method here, we have a formula, and what we're going to do is derive what that formula actually is. And then we're going to conceptually talk about what it is that this particular formula is doing. And so after we do that, then we'll get into the whole iterative process of actually doing calculations using Newton's method to try to figure out the one of the x-intercepts for a function that we're going to be considering. So for the derivation process, the first thing that we want to realize here is that really all we're doing is finding the x-intercept for the equation of a tangent line. Okay, so if we have some function, let's say have a function y which is equal to f of x, okay, then of course we know the corresponding derivative of that function is going to be f prime of x. If we are looking at our function at a specific point, let's just say if we're looking at it at the specific point, x sub 0, f of x sub 0, and we know that our equation of a line for our tangent line could be expressed in terms of the point slope formula of an equation of a line. Meaning I could rewrite it this way. Then all we need to do here is essentially rename what y sub 1 is, what m is, what x is, what x sub 1 is, and let y be 0. Okay? So if we do that, then when we solve for this x here, what we will essentially get is this formula, and I'm going to demonstrate that. So we're going to do the following. Let y equal 0. We're also going to let y sub 1 be f of x sub 0. We're going to let m be the derivative of our function at x sub 0. And of course, we know this as the slope of the tangent line. And that should be an n, not an m. And let's see, we have y sub 1, we got m. Yep, so we're going to let x be x sub n plus 1. And we are going to let x sub 1 be x sub n. Okay, and all this means here is that if I give you x of n, what we're trying to find is the next x value, which is x of n plus 1. And we're also assuming here that our point, so for this corresponding x value, that the point x of n plus 1, f of x of n plus 1 is on the graph of the tangent line. Okay, so with all that being said here, if I go and make these substitutions, I'm going to write them in a different color. So we're going to let this be 0, y sub 1 be f of x sub 0, let m be f prime of x sub 0. Let this x here be x of n plus 1, and let that x of 1 be x sub n. Then what this turns out to be is just 0 minus f of x sub 0 equals f prime of x sub 0 times, and in parentheses, x sub n plus 1 minus x sub n. And so from here, all we need to do is solve for x sub n plus 1. So what we want to do is solve for this particular variable here. So if we do that, then of course, first thing we should do is divide both sides by f prime of x sub 0. Okay? So if we do that, then this will be minus f of x sub 0 divided by f prime of x sub 0. And that will be equal to x of n plus 1 minus x of n. And then of course from here, if we add x of n to both sides, then we have x of n minus f of x sub 0 divided by f prime of x sub 0. And that is going to be equal to x of n plus 1. And so you see here, what we have is essentially the same formula that I had up here. Okay, same exact formula. So I don't know why I put, oh yeah, I know why I put x sub 0 though, because I put it there. Here, I guess to keep everything consistent, what I should have done here, and I'm gonna go ahead and correct this. Instead of these x sub 0s, we're just gonna put x of n. Yeah, because that'll kind of make everything go together. So let's say if we make this x of n, x of n, and we'll change this here. So make this x of n and x of n here. And then finally, we'll go ahead and change this. And so the reason why I'm doing x of n is because I don't want to just start plugging in, I don't want to plug in numbers. I just want to keep it as general as possible. Of course, we'll always start off with n equals 0, but just to keep it in general, I like to use n. And of course, I forgot to do that here, so that's why I'm having to correct myself. Okay, and then we have one more here. And so that way the n plus 1 will make sense with how we use the x of n in order to get the x of n plus 1. And I think I got that. So this is just x of n and x of n. And let's get these here. X of n and x of n. Right. All right, so I think I got them all changed up. So now you see how if we know what x of n is, then we use it to plug into the actual function. We use it to plug into the derivative of the function. And then from all that, we do x of n minus the quotient of the function divided by its derivative at x of n to find out the new x of n value. And what that essentially is the x-intercept of the tangent line that we found for our function at this particular point, x of n, f of x of n. So now that we understand where this particular formula comes from, I want to go over some key points about how to use this particular method, because sometimes it does not work, and we need to know when those situations will be, or that it won't work as planned. So you need to know when that's going to be. And then I'm going to demonstrate geometrically what is actually going on the graph of the example that we're going to do before we start doing the calculations. All right, so let's move forward here. So the two key points that I want you to know here is that, first of all, we need to select an initial x value that's going to be close to the root or close to the x-intercept that you're trying to find. Now, the question may be, well, how am I supposed to know that? Well, from a theoretical standpoint, if you're studying first year calculus, one of the important theorems that you have at your disposal is called the intermediate value theorem. And so the intermediate value theorem basically sets up the conditions to say that if you have a function that is continuous over a closed interval, that let's say if you have this closed interval from a to b for some function f of x that is continuous, then it guarantees that for all x values strictly in between x equals a and x equals b, that you're going to have at least one solution that looks like this. So in other words, if I select a value that is strictly within a and b, I know that this value c is going to have a corresponding y value. And this y value we're calling n, and this y value should be in between what f of a and what f of b will turn out to be. And one of the ways that we use this kind of judiciously is, instead of saying we want to find out what f of c equals n is, we say what is f of c minus n equals to 0. And when we use it in this form, what we are essentially doing is saying, hey, can you give me a situation to where I see a sign change in between what happens when I plug in a into my function and when I plug in b into my function, okay? Because if I have a sign change, let's say I have something that looks like this. This is the actual value c. If this is a and this is b, then of course this point and this point here, we'll have the point a f of a. We'll have the point b f of b here. And notice that f of a is going to be positive if this is above the x-axis, and f of b is negative if it is below. So all I have to do is be ingenious enough or clever enough to be able to figure out, well, I may not know that what this root exactly is, but I do know it's in between these two values. And I know that because when I plug in the value before what I think it is, or around what I think it is, I have a positive value. If I plug it after, plug in a value c after that, it'll be negative. Or of course you can have the vice versa case, okay? So that's one way of knowing. Of course, if you're looking at a graph and you're like, yeah, don't know exactly what it is, but I can just visually see that it's in between these two numbers, then of course you can start from there as well. But we normally use the intermediate value theorem if we don't even have a graph of the function or relation that it is that we're looking at. Now, the other thing that we have to watch out for is when this method fails, okay? And so this method fails whenever we have an x value that is a critical number of our function. So if you remember, a critical value or critical number of our function is a value c such that when we plug it into the derivative, specifically in this case, we're talking about when the derivative is equal to 0, okay? Now, of course, in the f prime of c does not exist case, of course, in this case, it won't work, but we probably wouldn't look for that in this type situation here. So we strictly keep up what's going on here. Now, remember that the derivative of this function at this x value is equal to 0. And if we go back up to our formula here, notice that we don't want f prime of whatever x value that we plug in to be 0. And of course, a critical value is a value, in this case, it is a value of x that we plug into the derivative and it actually ends up equaling 0. So we don't want that, okay? So if we go through the process of using Newton's method and it turns out that during the iterations that one of the x values that ends up getting calculated in to use is a critical value, Newton's method will fail at that point. Another thing that we want to avoid is picking values of x that are too far from the actual root, because if it's too far, then what we'll find out is the method will try to find the root that's closest to where we started. And of course, if we're too far and we have another x-intercept, then it will try to find that other x-intercept instead of the one that we're actually looking for, okay? So those are some things to keep in mind. So next, what we are going to do is geometrically try to understand what is going on whenever we use Newton's method in several iterations. So the picture of the graph that we are about to look at is a picture of this cubic function, x cubed plus 6x squared minus 2x minus 12. Okay, and so just going to look at this graph, and let's say we want to find out exactly what this root is right here. Okay. Let's say we want to know the exact value to within some margin of error. So the first thing that we would do is we would pick a value that's relatively close to this one. And of course, since we know that this root is going to be somewhere in between 1 and 2, I'm going to start with x equals 1. Okay? And so the main idea here is if I start at x equals 1, I want to find out what this corresponding y value is. And then after that, I want to find the tangent line that goes through this point. So if I was to draw the tangent line, it would look something like this. And my goal is to figure out what is the x-intercept of this particular tangent line. Well, it's right here. So once I find that, then notice here that 1 is going to be my x sub 0, so the initial value that I start looking at. When I go to this point here, I have x sub 0, f of x sub 0, so I'm finding that. For this tangent line here, I know that the slope of this tangent line is f prime of x sub 0, or in this case, f prime of 1. And then this point that I'm finding here is going to be my x sub 1, okay? Or the x-intercept for the tangent line. So once I find that out, I'll just note this here. So say when n is equal to 0, we have 1. And we would have whatever value that's right here. So since I don't know exactly what it is, I'm not going to try to figure that out for right now. All right, so main thing here is that now we have x sub 1, okay? So now I'm going to erase the rest of this, and we're going to start with x sub 1, and we're going to start this process over again. All right, so now, again, we're still trying to find this x-intercept here. But now we have our new value x sub 1, and so all we want to do is use x sub 1 to go and find the new corresponding y value for that. So that would be here. And so once we have that, then of course what we want to do is find a tangent line that's going to go through that particular point. And so that's going to look, I'm going to try to draw this. It's going to look something like this. And notice how my line is getting much, much closer to the actual x-intercept that I want, okay? So I'm going to zoom in here so that we can see this a little better. All right, so I've zoomed in, and now we see right where our tangent line is now intersecting the x-axis here. And so I'm going to go ahead and make a point here. So it is actually right there. And so that is going to be our new value x sub 2. Okay. So I'm going to erase the rest of this, start x sub 2 and do it one more time. And then, of course, from there, you'll probably get a good idea of how this iteration process from a graphical perspective works. All right, so now at this point, we have our x sub 2, and we're going to use that to find an x sub 3. So we're going to take this value here, and we're going to find the x sub, f of x sub 2. And I'll go ahead and erase that. I'll go ahead and erase this too. And so from here we have this point, and what we want to do now, we have this point, and what we want to do now is find the tangent line that will go through this point. So let me do this in a different color. So here, this tangent line will probably look something like that. And as you see at this point, I'm really close to what the actual root is. And of course, how close do I get? Well, that depends upon how accurate I want to be. And of course, I can make those decisions depending upon the application or the context in which I'm actually using Newton's method. So from a graphical perspective, this is essentially what we're doing. We're leveraging and exploiting what we know about the x-intercept of a line to basically get closer and closer to the x-intercept of the actual function that we want. Okay. All right, so now what we're going to do is do this whole scenario that I've just done, but we're actually going to use the Newton's method formula to be able to do it. And so we're going to go through a few iterations just so that you get a feel for how the calculations go. And then afterwards, I'm going to show you, I'm going to show you in Excel how it actually looks whenever we do these calculations there. And I'll also show you the actual code in the cells that I have. So for those of you that aren't taking, let's say, any one of my courses, you'll be able to at least know what the actual, what's inside the actual cells for the Excel file, so that you can kind of recreate this on your own. All right, so let's move on to the next thing that we need to do here. Okay, so what we're going to do now is actually do the calculations that we were talking about earlier. And so just like how we did last time, we're going to start off with x sub 0 with being 1. And I'm going to use this formula, x sub n plus 1 equals x sub n minus f of x sub n divided by the derivative of the function evaluated at x sub n to figure out what my x sub n plus 1 is going to be. And then we'll compare what we have here with the x sub n plus 1 with the x sub n. And of course, we just want to see how close these two numbers are. And the margin of error that I'm going to use here is that I want less than 0.001. So less than 0.1% difference in between these two numbers here. All right, so the first thing that I need to do, of course, in this situation, and I'll just go ahead and write it here, and then we'll talk about the actual calculations a little bit later here. So I want to find x sub 1. So that means I need to use x sub 0, f of x sub 0, f prime of x sub 0. And in this case, what that actually is I want to have 1 here. I want to have 1 here and have 1 here. So I need to find out what f of 1 is and what f prime of 1 is. So I have my function f and my function f prime. So when n is equal to 0, I'm just going to evaluate my function at 1 and evaluate the derivative of the function at 1. And of course, if I was to plug in 1 here, then I would get 1 plus 6 minus 2 minus 12, and I would end up with a minus 7 when I plug in 1 everywhere where I see x. For the derivative, I would get 3 plus 12 minus 2, and that will give me 13. And so this would mean that my x of 1 now would be 1 minus, and I'll rewrite the formula here. So I know that in this case, my x of n is just 1 minus f of 1 is a minus 7 divided by f prime of 1, which is 13. And of course, subtract the negative is the same as addition. And this would end up being 1 7/13, which is the same as 20 over 13. And if we want the decimal value for 20 over 13, that's roughly about 1.5385. So 1.5385. And so I'm going to go out to 4 decimal places, since the margin of error that I want is going to be within 3 decimal places, basically. And if you forgot about that here, I want it within, really more like within 2 decimal places, but I'm just going to use 4 numbers after the decimal place just to make sure that I'm as accurate as possible. All right, so we see here that x of 1, we're going to let it be 1.5385. And so now we start that process over. So now we say we have when n is equal to 1. So now we want f of x of 1, or f of 1.5385. And we also want f prime of x of 1, which is going to be f prime of 1.5385. Okay. And whenever we plug in that particular value, 1.5385, into our original function, I'm just going to tell you what we get. It'll be 2.766497. Okay. And when we plug in that same number into the derivative, we will get 23.562947. Okay. And so now we need to figure out what our x sub 2 is going to be. And remember that from the formula here, since we want to find x sub 2, that means we have to use x sub 1. And our x sub 1 is 1.5385. So here this will be 1.5385 minus, and then we use our 2 numbers here. So that's 2.7664957. All that divided by 23.562947. And after we do our calculations here, the result that we get here is 1.4211. Okay. And so that will be our new value here. Okay. Now, one thing I haven't done yet, and I'll go ahead and do this now, is we'll talk about the error in between the previous x sub n value and the current x sub n value. In other words, we'll talk about the difference in between x sub n and x sub n plus 1. Okay, so for the current situation that we have, the difference in between x sub 2 and x sub 1, and we're looking at this in terms of absolute value. Really don't care if it's positive or negative. And I'll go ahead and calculate that right quick. The difference in between those two numbers here will be about 0.1174 from each other, okay? So I need something with at least 0.00 and then something here, okay? And more than likely, since I said 0.001, I would like to have something that is the difference will be 0.001 or less. So I would probably look for something like be 0.00098 or something lower than that. Okay, so that's kind of what we're looking for here. Once I'm done doing this last iteration here, because I think we'll be almost close enough at that point, I'll go ahead and list everything and calculate all the errors then. Okay. So here at this point, I think after doing 2 rounds of this, you kind of see what's going on. So what I'm going to do now is just list the final results that we get along with the errors so that you can see how all this starts to work here. So we have our initial x sub n value, which is 1. We got 1.5385 for the x of 1. And then after that, we use the same value here for the n equals 1 iteration. And so from there, we got 1.4211, okay? And so we use that here. And so we haven't gone beyond that, but if we did, this is what we would get. So the next iteration would give us 1.4142, and then we would use that for to start off the n equals 3 iteration. And what we will find out is that here we would get within our margin of error that we want, because it would just be 1.4141 at that point. And of course, the margin of error here would just be 0.5385. For this other one would be 0.1174. For the next one, it would be 0.0069, and of course not quite there. We would need something 0.001 or less, but the next iteration ends up being 0.0001, and of course that is well below this 0.001 that we need. And so we see that the x-intercept for this particular function is roughly about 1.4141, okay? And so that is how Newton's method is used to be able to find solutions to equations, in particular whenever we're trying to find roots of equations. So the last thing that I'm going to do now is actually show you how we could actually do this in Microsoft Excel so that you won't have to do all these calculations by hand all the time. Once you kind of get an idea of how this works, to start off, then Excel allows you to just copy and paste to make this relatively simple to get the results that you're looking for. All right, so now what I have here is this actual process that we've just done, programmed in Excel. And so what I'm going to do is kind of show you how to do this from scratch. Let's see, I also want to go ahead and show you the formulas for those of you that just kind of want to just take a picture of this and use it later. So let me just go to formulas. Probably need to, yeah, Okay. And so this is what the actual formulas look like. Notice that this cell here, I'll put my initial guess in right here. Notice that the function that I had here is the same exact one that I used in the example. And notice that just like the graph showed me, I had to know that the root that I was looking for was in between 1 and 2. And so notice here that all my calculations start off with C10. So in this first column here, notice that I'm just typing in this function where everywhere where I have X, I type in C10. Then I know what my derivative of this function is. I didn't type it here, but you can do it yourself and then figure out what that is and type it in. And then of course, after that, this is the cell where I actually calculate the new value of X that I want to use. And it's just really just C10 here minus the quotient of f of x of n and f prime of x of n. So I have that here, and that gives me my new value. And then here I just compare the difference in between what I'm calculating here and what my initial guess was. And of course here I've put in some code to basically say, hey, if I get to that 0.001, or if I get below that, then I basically want to tell myself I can stop. If I don't get there, then I want to keep on going, okay? And so all I did here for this is I really just wrote in all of these, and then I just copied and pasted, okay? And so, and I'm going to actually demonstrate that. All right, so let's go back to the formula view here, and I'm going to erase all of these just so that you can kind of see how this works. So once I was here, then of course, let's see, I took this and I said, all right, well, sorry, this one, because this is going to be the new value that I need. So I'm going to copy that, paste it here. Oops, sorry. Yeah, okay. Yeah, I can't do it like that. Sorry. I'll just type it in. So this particular cell here is F10. So I'll just type it in that way. And then after that, for these other 3 here, well, actually for the rest of these, I'll just copy and paste. And you see how it just automatically does the calculations for me. And then at that point, I'm just going to keep on copying lines and pasting until I get to the yes. And you see, once I get there, I know that I can stop, because the current x of n that I have, which is going to be this cell right here, the one with the 1.4142136, this gets me within 0.001 of what the actual root is, okay? And so this is how Newton's method actually works, okay? So hopefully this video gave you a good idea of what Newton's method actually is, how we derive it, graphically what's going on when we actually do the iterations to find our x-intercept that we're looking for, as well as how to use it in Microsoft Excel, or implement Newton's method in Microsoft Excel so that you can do these calculations without having to do them by hand. So I hope this helped. Take care.